Okay, just a quick check. You can see my screen and also see the screen moving like this. Yes. Okay, good. Thank you. Let's begin with this thing. Complex numbers. This is the next topic that we've got now. First of all, what are complex numbers? You would have seen equations, quadratic equations before at some point. That when we solve them, you end up getting a negative number inside square roots. When you have a negative number inside square root, you can write that in terms of this number that we define as iota. It has a value of square root of -1. We say whenever we have square root of -1, we would write that as iota, right? So we have defined this number called iota like this. It's represented by I. Whenever we have square root of a negative number, we can write that in terms of iota. How would you do that? So in this case, when we apply the quadratic formula on this equation, we end up getting this. Now, square root of -16, we could write that as square root of 16 times square root of -1. And square root of -1 can be written as iota. So it becomes square root of 16, which is 4 times iota. And then we simplify that, we end up getting 3 plus minus 2 iota. That means 3 plus 2 iota and 3 minus 2 iota. These are the two solutions of this equation. So earlier when we used to say that this equation does not have any solutions, we meant that it has no real solutions, but it does have complex solutions. Okay, so it has two complex solutions like this. Now, these complex numbers that we've got, this is the standard form of complex numbers. We call this Cartesian form. You need to remember this name as well. Sometimes they refer to this name in questions as well. You need to know what this represents. X plus y iota, this is the standard form for complex numbers. It's also known as Cartesian form. Now, it has two parts. One part is real part and the other is imaginary part. Real part is the one that does not have iota with it. This is the imaginary part that has iota multiplied with it, right? So x is real, x is the real part, y is the imaginary part. This is notation. There's some notation that you need to know about. If they say RE of z, that means real part of z. In this case, if the number z is equal to 5 minus 3 iota, real part of z is equal to 5, and the imaginary part of z, that is -3, right? So imaginary already incorporates that that it will have an iota with it. So we say imaginary part of z, that's just -3. These are notations that we have for real part and imaginary part. Now, we often represent complex numbers using letters like Z, U, V, because X and Y, we use them for real numbers generally. So for complex numbers, it's a convention that we use Z, U, V letters like these, other than X, Y. Now, we have another terminology that we call conjugate of a complex number. If you have a complex number like this, 5 minus 3 iota, there's another complex number that's defined corresponding to that, and that's 5 plus 3 iota. We say that's the conjugate of this number z. It's represented, it's denoted by this notation z star, z asterisk. So if we have x plus y iota, the conjugate of that z asterisk, that is x minus y iota. What happens is the imaginary part's sign is flipped and it becomes the conjugate. If you have two numbers like this, one is -4 plus 7 iota, and other is -4 minus 7 iota, you see the imaginary parts have different signs. These are conjugates of each other. Together we say it's a conjugate pair. Okay. Then we need to know how to evaluate powers of iota. If it's iota power 1, that's just iota. Iota square, what would that be? Since iota is defined as square root of -1, square root of -1 whole squared, iota square root gets cancelled, and we have -1 left from that. Now, this is a very important result that we will be using in almost every single complex number problem. That square of iota squared is -1, right? So iota squared is a real number. If you were to evaluate higher powers, sometimes you have to evaluate iota cube as well. How can you do that? Iota cube can be written as iota squared into iota. Then iota squared is -1, so it becomes minus iota. Iota raised to power 4, that's just iota raised to power 2 into iota raised to power 2. Iota squared into iota squared, that becomes -1 into -1, and that's +1. That's this. And similarly, you can go on like this. It's a cyclic pattern. It keeps repeating after this. Iota raised to power 5 is iota, and power 6 would be this again, power 7 would be this again. However, we would just need to go up to iota cube generally. So you see, odd powers of iota are imaginary, even powers of iota, they are real numbers. So this is real, this is real. Okay. Now you need to be able to add and subtract complex numbers. Addition subtraction works like it works for any expressions in terms of x, y, for instance. Just add and subtract the like terms. The real parts get added and subtracted to each other. Imaginary parts get added and subtracted to each other, right? You can see that here. Multiplication, when you have two complex numbers that are multiplying, we do multiplication like we normally do as well. We multiply every term of the first bracket with every term of the second bracket, and we get an expression like this. However, after multiplication or division, the final result that we want, that has to be in this form, x plus y iota. Now, in this multiplication, we end up getting iota squared. So what we do is we don't leave it as iota squared. We would have to convert it to -1 first of all. So we say iota squared is -1. Replace that with -1, and then you input that here, simplify everything, and that gives you 45 plus 10 iota here. Okay, that's how multiplication works. If you have to divide two complex numbers, how does that work? If you have 4 minus 3 iota and 6 plus 7 iota, you want to divide one complex number by another complex number. Let's say you want to do u over v. How would that work? 4 minus 3 iota over 6 plus 7 iota. The final result that we want has to be in this form, x plus y iota. Now, in this case, we have iota in the denominator. We don't want iota in the denominator. We only want it in the numerator in this form, x plus y iota. So the point is we want to get rid of iota from the denominator. The way to do that is, this process is called rationalization. What we do is we multiply and divide by the conjugate of the denominator. Now, what's the conjugate of the denominator? This is 6 plus 7 iota, right? The conjugate of that is 6 minus 7 iota. We multiply and divide that fraction by the conjugate. And what happens when we do that is we have a plus b here into a minus b. When we do a plus b into a minus b, we end up getting a squared minus b squared. So we only have iota squared in the denominator, and we know iota squared is a real number. So that can be replaced with -1. And that's how we can get rid of iota from the denominator, right? And then the numerator gets simplified like we normally do. We just multiply these two expressions. We have iota squared there. We'll replace iota squared with -1. Simplify everything at the end. We write the real part separate, imaginary part separate. 3 over 85 minus 46 over 85 iota. That's the result that we end up getting when we multiply, when we divide these two complex numbers. Okay. Now, why did we multiply and divide by the conjugate? To get a square minus b square here, because that gets rid of the iota. When you have even power of iota, it becomes real. If you just had something like this, 4 over iota, for instance, in this case, if you want to get rid of iota, or let's say 4 over 3 iota, if you had something like this, one way to do this could be that you multiply and divide by the conjugate of the denominator. The conjugate of 3 iota, what would that be? That would be -3 iota. You could say multiply and divide by -3 iota. However, in this case, it's much simpler to just multiply and divide by iota, and that will be sufficient because all you want is that you have iota squared in the denominator. So if you just multiply and divide by iota, that will be sufficient in this case. That gives you 4 iota over 3 iota squared, and that gives you 4 iota over -3. So we've gotten rid of the iota from the denominator. However, when we have both real and imaginary parts, then we can't just multiply and divide by iota. Then we have to multiply and divide by the conjugate, and that will eliminate iota from the denominator. If you have any other power of iota, for example, you're saying if we had iota cube in the denominator, we would convert that. First of all, we'll say that that's iota squared into iota, and that simplifies to minus iota. So that will simplify to iota. All right. Okay, now let's move on. Two complex numbers, when are they equal to each other? When two complex numbers are equal to each other, their real parts have to be equal and their imaginary parts have to be equal. Now, this is very important. You will see later on, you will get equations in which we'll have one complex number on the left side, another complex number on the right side. If they're equal to each other, we would say the real part on the left and right, they are equal to each other, and the imaginary parts on both sides, they're also equal to each other. So that means x equals a and y equals b in this case. Okay, now keep this in mind. We'll have a look at some examples. Let's say you've got a quadratic equation like this. You want to find the values of c. How do you do that? It's a quadratic equation. For solving quadratic equation, you can just apply the quadratic formula, input values in this, simplify everything. Now, generally, for equations that have real answers, it's sufficient generally to just input values in the formula and write down the answers. But in complex numbers, it's necessary for you to show the working. You will not get marks if you do not show working in the exam. So you have to make sure that you show all working and clearly show the examiner how you're converting square root of something negative to iota. This step is very important. Okay, and then you simplify that and you get the result from that. Okay, take another example. So you can sometimes have equations like these as well, where you have iota in the equation itself. So in this case, we've got iota in the equation. But it's a quadratic equation still. How do we solve this quadratic equation? Input values in the quadratic formula. When you do that, inside the square root now, you get 4 iota squared plus 20. You simplify that, and you're not getting any negative number inside the square root in this case. However, you have iota already outside here. You've got iota outside here already, right? So you just simplify this, and you get the result. These are the two solutions that we're getting from this: 2 plus iota and minus 2 plus iota. Now, notice one thing. In the previous example that I showed you, in the very first example that I showed you, I solved this equation. I got two solutions from that: 3 plus 2 iota, 3 minus 2 iota. Both of these solutions were conjugates of each other. You see, the equation only had real coefficients. There was no iota in that original equation. In this case, when I solved these two equations here as well, when I solved this equation, I got two roots. They were both conjugates of each other again. In this case as well, the original equation did not have any iota in it, right? So it looks like a pattern that we'll talk about in a few minutes, that when we solve polynomial equations like these, their answers, if there are any complex roots, they always occur in conjugate pairs like this. However, there's a condition for that there should be no iota in that equation. When we had iota here in this case, the solutions that we got here, they were not conjugates. In this case, the real parts have different signs, but the imaginary parts, they have the same sign. So these are not conjugates, right? So in this case, that does not happen. Now, keep that in mind. We'll talk about that in a few minutes. Let's have a look at another example. We have two complex numbers, w and c. They satisfy this relation. Given that z is equal to 1 plus iota, find the value for w. How do you do that? You can input z equals 1 plus iota here. You do that. That simplifies to this. Now you've got iota squared in the denominator. You first have to simplify that. That becomes iota minus 1 plus 2. And then you've got one complex number in the numerator, another in the denominator. You want your final answer in x plus y iota form. So how do you get rid of the iota from the denominator? You multiply and divide by the conjugate, simplify everything, and you get the result from that. But the second part says, given instead that w equals z, find the value for them in complex numbers as well. You've got w equals z plus iota over iota z plus 2. That's one equation that we've got. And we have another equation that's w equals z. We can put w equal to z here, and that gives us this. Then multiply this denominator on the left side, and that gives us the quadratic equation. Now it's a quadratic equation. We can use the quadratic formula, input values in this, solve that equation, and we get the result from that. It becomes a bit lengthy, but we get two answers from this. However, in this question, they said the real part of z is supposed to be negative, right? In our answers that we got here, you can have a look at this working. One of them had a positive real part and the other had a negative real part. They said that the real part is supposed to be negative. So we only consider the one that has negative real part, and we say that's our final answer. Okay. So in complex numbers as well, sometimes you may have to solve simultaneous equations like these, and then they can become quadratic like this as well. And you just solve them like a normal quadratic. When you have a negative number inside the square root, you would just write that in terms of iota. Okay. Now, times what by conjugate? I'm not sure what you mean. Let's discuss that at the end. Let's discuss that at the end. There's no W here. We've already put W equal to Z, right? So the W is eliminated. There's no W anymore, right? Let's talk about that at the end, okay? Let's try to be a bit quick. The complex number W is such that the real part of W is greater than Z, and we have another equation that's W plus 3W conjugate equals iota W squared. Now, in this case, we have this equation. This also looks like a quadratic equation. However, the problem is we've got two unknowns here. We've got W and we've got W conjugate. There are two unknowns, right? When we have two unknowns and only one equation, we can't really solve that, right? In equations where you have both a complex number and its conjugate together, what you do is you input input one of those complex numbers as x plus y iota, and the other, the conjugate, that would be x minus y iota, right? So you input these values like this because you cannot solve it directly. You've got two unknowns. What you do is you say if w is equal to x plus y iota, then w conjugate is going to be x minus y iota, right? You input those things here, simplify everything. Now, after you've done the simplification, what happens is you end up getting this on both sides. On the left side, you have 4x as the real part. On the right side, you have minus 2xy as the real part. On the left side, you have minus 2y as the imaginary part. On the right side, when you take iota common from the terms that have iota in them, x squared minus y squared is the imaginary part. Now, if these two complex numbers are equal, the one on the left side, the one on the right side, then that means the real parts are supposed to be equal to each other and the imaginary parts are supposed to be equal to each other. We get two simultaneous equations from that and we solve them simultaneously to get the values of x and y. In the question, they said that the real part of w is supposed to be positive, so we only consider the possible answer in which the real part, which is x, is positive, and we ignore the other answer. So this is a standard method that we have for problems like these. Whenever in an equation you have both a complex number and its conjugate, you do a substitution like this. You put that complex number equal to x plus y iota and its conjugate equal to x minus y iota. You'll have one complex number on the left side, one on the right side. You do comparison and solve that equation further. Now, we talked about this earlier, roots of polynomials. For any polynomial, this is a standard rule that we've got. For any polynomial that has real coefficients that do not have any iota in them, if there are any complex roots, they always occur in conjugate pairs, right? If the equation does not have any iota in it, then the solutions that you get, if they are complex, they always occur in conjugate pairs. Okay, so if you know one root, for instance, for example, if one root is 2 plus 3 iota, you know for sure that 2 minus 3 iota is also going to be a root, right? Now, since they occur in conjugate pairs, the number of complex roots that you would get would always be even in such cases because they are going to occur in pairs. So you can have 2 complex roots, 4 complex roots, 6 complex roots like this. And that also tells us that the total number of roots of any polynomial is always equal to the degree of the polynomial. So if you have a quadratic equation, for instance, it will always have 2 roots. Earlier, we used to say that we would either have 2 roots or no real roots. When we have no real roots, then that means you have 2 complex roots. So for any polynomial, if it's a cubic polynomial, it always has 3 solutions. If it's a quartic polynomial, quartic is power 4 polynomial. In that case, you always have 4 roots. Now, some of them may be complex, some of them may be real, but the total number of roots is always going to be equal to the degree of the polynomial. So, for example, this is not something that you need to memorize as such, but just for understanding. If you have a quadratic equation, for instance, the total number of roots is always going to be 2. And now, one possibility is that both of them are real and none of them are complex, or both of them are complex and none is real. 2 complex and 0 real. These are the 2 possibilities that we can have. We can't have 1, 1. Similarly, if you have cubic, then the total number of roots is 3. One possibility is that all of them are real, or 2 complex and 1 real. The number of complex roots that can never be odd in such polynomials where the coefficients are real. Okay. Now, why is that important? Let's have a look at this example. Let's suppose you've got this equation z cubed minus the 3z squared minus 3z4 minus 4 equal to 0. And you're given that z equals 4 is a solution of this equation. What you need to do is you need to find all the complex solutions. So you have a cubic equation. How many solutions is it going to have? 3 solutions. You're given one solution, that's the real solution. How do you find the corresponding complex solutions? Now, if z equals 4 is a solution, that means z minus 4 is the factor of that polynomial. What we can do is we can do polynomial division. We can do division, long division, divide that polynomial by z minus 4, and we get a quotient from that, and that's the other factor that we have. Now, that's the other factor. You equate that to 0. This was the polynomial, this equal to 0. This was the equation. We have factorized that now. Z minus 4 into z squared plus z plus 1 equal to 0. We say either z minus 4 is equal to 0 or z squared plus z plus 1 equal to 0. We can solve that quadratic equation, find the value of z from that. We get two values of z, and these are the complex roots that we were looking for. So in complex numbers, the one other topic that is also tested sometimes is polynomials. So you will need to do polynomial division sometimes like this. You'll have one solution given, you'll have to find the other solutions. In this case, the real solution was given. So we said this is the factor. We did long division and found the other factor and the other solutions based on that. Let's look at this example now. Now you're given that you have this polynomial equation. It has one root, that's 1 plus iota square root of 3. Now, given this, you need to find the other two roots. You're given one complex root in this case. In the previous case, you were given the one real root. This is one complex root that's given. Now, if this is a complex root, look at the polynomial. There's no iota in the polynomial. All the coefficients are real. That means if this is one solution, then one other solution has to be its conjugate. So that's 1 minus iota square root of 3, right? Now, you've got two solutions now. How do you find the third solution now that's remaining? We could say, think about this. How do quadratic equations work? If you have, or any equation, any polynomial equation works. If you have an equation like this, you factorize that, you get this, x minus 3 into x minus 4 equal to 0. And then you say either x minus 3 equals 0, x minus 4 is equal to 0, and you get x equals 3 or x equals 4 from that. Now, if you know what the final answers are, and you want to go back to the original equation, how do you do that? You can go backwards like this. You can say, okay, x equals 3, x equals 4. Let's go one step back. And that gives you x minus 3 equal to 0 or x minus 4 equal to 0. And then you multiply those two factors, x minus 3 into x minus 4. And then you go back further and you get that quadratic factor that you started from. So if you have solutions given, you can go back to the original quadratic factor using this method like this. We can do something similar here with these complex roots. We know that these are the solutions. These are the solutions. What are the factors going to be? We bring these terms to the left side. We bring 1 plus iota square root of 3 to the left side, 1 minus iota square root of 3 to the left side. And that gives us that this is one factor and this is another factor. These are two factors. And now what's the next step? We multiply these two factors, right? Just like we did here. When going backwards, we could multiply these two factors so that we can get back to that quadratic factor that we had. So we multiply these two factors now. It becomes z minus 1 minus iota square root of 3 into z minus 1 plus iota square root of 3. And now you have to do this multiplication. Now, since these roots are always going to be conjugates, when this multiplication will always be of this form, it will be a minus b into a plus b. Right? So you can do this multiplication directly like this. You could say z minus 1, for instance, in this case is a, and then iota square root of 3 is b. So this is a minus b into a plus b, and you know that will become a squared minus b squared. The longer method would be that you multiply every term from the first bracket with every term in the second bracket. So z into this, into this, into this, that will be 3 terms. And in total, that will become 9 terms. That's a lot of calculation to do. You could do that if you wanted. But a simpler way of doing this would be to think of it like this, a minus b into a plus b, and that becomes a squared minus b squared. Right? Simplify this further and you get this quadratic factor. So now you know that polynomial has this quadratic factor. How do you find the remaining factor now? You divide that polynomial with this quadratic factor, and you get that linear factor that you were looking for, and that will give you the third solution, right? So this is how you can solve problems like these. When you have one complex solution given, the other solution is going to be a conjugate, and then you multiply those, you make factors from them, multiply those two factors, you get a quadratic factor that would not have any iota in it. Iota will get eliminated. Then you can do division to find the other remaining factor. This is one way of doing such problems, and you must know this method. But there's an alternative that will work in most problems like this as well, and that is sum of roots and product of roots formulas. Now, what is sum of roots and what is product of roots? Let's say you've got an equation like this: 3x squared minus 21x plus 36 equal to 0. You solve this equation and you get two roots from this: x equals 4 and x equals 3. Now, if you add 4 and 3, you get 7. This is called sum of roots. If you multiply 4 and 3, you get 12. This is called product of roots. So for this equation, the sum of roots is 7 and the product of roots is 12. Now we actually have formulas that we can use to find sum of roots and product of roots of any polynomial directly without actually solving that. We could find sum of roots and product of roots directly. How does that work? For sum of roots, we have this formula that's minus b over a. We could use that to find the sum of roots. For example, in this case, this is ax squared plus bx plus c. The value for a is 3. The value for b is minus 21. Put that in minus b over a, and that gives you 7. That's the sum of roots. The product of roots is given by the constant term divided by the first term. The constant term divided by the first term. So that's c over a in this case, and that gives you 12. That's the product of roots. Now that's very helpful, but let's generalize this for bigger polynomials, and then I'll tell you how to use that. For quadratic, and for any other polynomial, for cubic, for power 4, power 5, the sum of roots has the same formula. That will remain minus b over a, minus b over a, minus b over a. So b is the second highest coefficient of the second highest power, and a is the coefficient of the highest power, right? So this formula for sum of roots will remain minus b over a. But for product of roots, the formula is the constant term divided by the first term. Constant divided by first term. And there's another detail there. When the degree of the polynomial is even, then the formula has a plus sign with it. If the degree of the polynomial is odd, the formula has a negative sign with it, the product one. The sum formula remains the same, that's minus b over a, minus b over a, minus b over a. For the product, if it's in even degree, the formula has a positive sign. If it's an odd degree, the formula has a negative sign. Okay. In general, you could say something like this: if you have a polynomial of this form, ax raised to power n plus bx raised to power n minus 1, and so on, it keeps going on until you have the last term, that's the constant, whatever that is. Sum of roots is given by minus b over a, and product of roots is given by z over a. It will be plus z over a if it's an even degree, minus z over a if it's an odd degree, right? These are the general formulas that you can use. Now, how are they helpful? Look at that same example again that we saw earlier, and we had to do multiplication, find the quadratic factor, and then do long division. And after that, eventually, find the other factor and find the other solution that we got there. But all of that could be done much quicker. We have this equation 2z cubed minus z squared plus 2z plus 12 equal to 0. That same polynomial, it has this solution. We know that one other solution is going to be the conjugate. That's 1 minus iota square root of 3. And now we know this is the polynomial. The sum of roots of this polynomial is given by minus b over a, right? We know that a is equal to 2, b is equal to minus 1. In this polynomial, this is b, this is a. Sum of roots is minus b over a, so that's minus into minus 1 over 2. That becomes plus 1 over 2. And now we know one root, that is 1 plus iota square root of 3. The second root, 1 minus iota square root of 3. The third one is one that we do not know. We call that z3, and we just find the value of z3 from this equation. That turns out to be minus 3 over 2. That will be at least 4 marks, maybe 5, 6 marks question. You can do this directly like this, much quicker, much more efficient, and gets you full marks. That's an alternative that you can use in this problem. Okay, let's move on. Then you have Argand diagrams. To represent complex numbers on a diagram, we have this a diagram called an Argand diagram. It's very similar to the Cartesian plane x-y axis. What we do is to represent complex numbers graphically, we have this diagram in which the horizontal axis represents real numbers, the vertical axis represents imaginary numbers. So if I had to plot any point, for instance, 3 plus 4 iota, that would mean it's 3 on the horizontal axis, 4 on the vertical axis. That's the point W. If we had to plot another point, for example, 3 iota, where is that going to be? And the real part is 0, imaginary part is 3, that will be this point here. If it's only a real number, for example, -2, that will be here on the horizontal axis, and so on. You can see that. Now, on an Argand diagram, we have some terminologies that are there for any complex number. Number one, modulus of a complex number. Then we have argument of a complex number. What's the modulus of a complex number? Modulus is the distance from origin of the point representing the complex number on an Argand diagram. Distance from origin. So for example, if you have this point z 4 minus 3 iota, that's somewhere here. What's the distance from origin? You can find that using Pythagoras. In general, we could say z is equal to, if we have a complex number z equals x plus y iota, the modulus of that is going to be given by square root of x squared plus y squared. That comes from Pythagoras. So for example, if we had 4 minus 3 iota, what's the modulus of that? That's going to be square root of 4 squared plus 3 squared, and that turns out to be 5. That's the distance that this complex number has from the origin. Okay, so modulus of a complex number, that's distance from origin. It's calculated using this formula, square root of x squared plus y squared. Now, the notation that we have for this is this, the modulus sign, or it's also represented by the letter R, as we will see later. Then another thing is defined, that's argument of a complex number. What's argument of a complex number? Argument is the angle made with the positive x-axis by the line joining the complex number and origin. So for example, if I have this complex number 4 plus 5 iota, now that's going to be here 4 plus 5 iota. If I were to draw a line that joins this point with the origin, that's this blue line, the angle that this line makes with the positive x-axis, that's this angle, that is the argument of this complex number. Now, how do you find this argument? You can think of this right angle triangle. You're looking for this angle here. You can use tan for that, right? This is perpendicular. This is the base. Tan theta equals 5/4, and that gives you the value for theta. That's 0.896. Always use radians in general in paper 3, unless a question specifically uses degrees. You will always be using radians. In integration, differential equations, iteration, complex, in these topics at least, you always have to use radians. So this angle turns out to be 0.896, and that's the argument of this complex number. Now, there is a range that we have for argument, and that is that argument is always supposed to be between minus pi and plus pi. So that's the convention that Cambridge uses, that whenever you write an argument, you would write that within this interval from minus pi to plus pi. Now, what does that mean? It's going from, this is 0, this is pi. On the positive side, this is where the interval ends. If you go in the third or fourth quadrant, you'll have to go from the negative direction. That means any complex number in the first or second quadrant, it will have a positive argument, and in the third and fourth quadrant, it will have a negative argument. Let's have a look at some examples for that. Let's say we have a complex number that looks like this, -2 plus 2 under root 3 iota. How do you find the argument of this? Remember, argument is the angle from the positive x-axis. That's this yellow line that you see here. Now, -2 plus 2 under root 3 iota, which quadrant is this in? The real part is negative, imaginary part is positive. It's going to be on the left side here, right? Top left, that's the second quadrant. That's where the argument is going to be. We are looking for this angle. That will be the argument. This is where the complex number is going to be. The argument is going to come from here, like this. Now, how do you find this? You can think of this right angle triangle. You find the basic angle first of all. It's called this basic angle alpha. Now we know the base of this triangle is 2. The height of this triangle is 2 under root 3. So we say tan of alpha that equals 2 under root 3 over 2. So essentially what we'll do is we'll divide the y component with the imaginary part with the real part like this, ignoring the sign because we're just looking for the basic angle. Basic angle in this case turns out to be pi over 3. What's the argument then? We find the argument from there. From the positive x-axis, that becomes pi minus pi over 3. That's 2 pi over 3. Similarly, if you were in any other quadrant, if it's minus 7 iota, in which quadrant is that going to be? Real part is negative, imaginary is negative. That means left and down. So it will be in the third quadrant. Now, in the third quadrant, we can find the basic angle. Let's call this angle alpha. How do you find that? The perpendicular and the base both are the same in this case, 7 and 7. You say tan alpha equals 7 over 7. The basic angle turns out to be pi over 4, right? That's the basic angle. And then what's the argument going to be? Remember, the interval is from minus pi to plus pi. So if we go from this side, it will go outside the interval. So we'll have to go in the negative direction. This will be the argument. We can say that's pi minus pi over 4. But since we're going in the clockwise direction, you put a negative sign with that. So that's negative 3 pi over 4. That's the argument that we get from this. So first of all, you find the basic angle and then look at which quadrant it is in. Based on that, you write down the argument. If it's in the first or second quadrant, that's going to be positive. If it's in the third or fourth quadrant, that's going to be negative. This is what happens when it's in the fourth quadrant. 3 minus 2 iota, that means right and down. That's fourth quadrant here. Again, you find the basic angle. How do you find the basic angle? Divide the imaginary part with the real part, and that's equal to tan alpha. You'll get the value of the basic angle. Now, since it's in the fourth quadrant, you have to go clockwise, and that's the angle that you get. That's the argument, minus 0.588. That's your argument. This is the general method that you can use. Find the basic angle, use the positive values of y and x, find the basic angle, and then look at which quadrant you are in. Write down the angle within this interval. If it's first or second quadrant, the argument is going to be positive. If it's third or fourth quadrant, the argument is going to be negative, right? So that's how you find arguments. Now, using modulus and argument of a complex number, we actually get two other forms of complex numbers, and we call them modulus argument form, or sometimes we can call them polar forms as well. Now, what are these forms? This was the Cartesian form, the first one that we did already, x plus y iota. There are two other forms of writing complex numbers that you need to remember. They're not given in the formula sheet. They're standard forms that you need to memorize. R into cos of theta plus iota sine theta, and r e raised to power iota theta. Now, there's some background to this, where they come from, but that's not relevant for us right now at this point in a revision class. So we have to remember this, right? R into cos theta plus iota sine theta, and r e raised to power iota theta. Now, in these forms, R represents modulus, theta represents argument, okay? So you can write any complex number in these three different forms. Now, how do you get to those forms? How do you write a number in those forms? For example, if you have something like this, z equals minus 2 under root 3 plus 2 iota. If you want to write this number in those other two forms, you need the value for the modulus and the value for the argument. Now, how would you get that? Like using the methods that we discussed before. Use the modulus formula, square root of x squared plus y squared, and that will give you the modulus. That turns out to be 4 in this case. That's the value for r. Find the basic angle. This complex number is in the second quadrant. In the second quadrant, real part is negative, imaginary part is positive. So it's in the second quadrant. You find the basic angle, and that turns out to be pi over 6. Based on that, you can write down the argument. The argument is 5 pi over 6. Once you have that, you can say this number could be written in those two other forms, r into cos theta plus iota sine theta. That would become this. Just input values in place of r and theta, or r e raised to power iota theta. That would become this, right? So you can write that in these two different forms like this. How do you do the other way conversion? For example, if you have the modulus argument form given and you want to go back to the Cartesian form, if you have the cos and sine form like this, in order to go from this form to x plus y iota, you can just put this on your calculator, put cos pi over 3 in your calculator, and that will give you 1 over 2. Put sine pi over 3 in your calculator, that will give you under root 3 over 2. And then just simplify this and you get the result, right? So other way around is pretty straightforward. You just have to simplify this cos pi over 3 evaluate that on your calculator, and similarly for the other one. What if you have the e power iota theta form given? How do you go from this form to the Cartesian form? Now, first of all, you figure out what's the argument in this and what's the modulus in this. How do you do that? This is the original complex number that you're given. Compare it with the standard form, r e raised to power iota theta. What is coming in place of r? In place of r, we've got 6, so that's the modulus. In place of the argument, we have minus 4 pi over 3. You see, you have the negative sign there as well. That's going to be part of the argument. That's minus 4 pi over 3. That's the argument. So now we have this form. In this form, we have the modulus and the argument. What we do is, if you want to convert it to x plus y iota form, first of all, what we do is we write this in the cos and sine form, right? In the cos and sine form, you input the value for r is equal to 6, theta is equal to minus 4 pi over 3, and then just put this on your calculator, put this on your calculator, put this on your calculator, evaluate them, get these numbers, and then just simplify this, multiply 6 inside, and that eventually gives you this complex number in the Cartesian form, right? That's how this conversion is done. Yes, you always use radians here. Always use radians. Do not use degrees. Now, from these new forms, if you had to find modulus and argument, we already talked about e power iota theta form earlier. So if you had 8 e raised to power iota into 2 pi over 3, 8 is the modulus and 2 pi over 3 is the argument. If there was a negative there in the power, that would also be part of the argument. We would say the argument is negative in that case. What about this cos and sine form? So for example, if I had something written like this, what's the argument in this form? 3 into cos of pi over 6 plus iota sine of pi over 6. Compare it with the standard form. In place of r, we've got 3. In place of theta, we have pi over 6. So we say the modulus is 3 and the argument is pi over 6 in this case. But sometimes what happens is you end up getting something negative like this. Cos of 3 pi over 4 minus iota sine of 3 pi over 4. What about this? The standard form that we have looks like this: r into cos theta plus iota sine theta. Now, how can this number be negative when it's supposed to be positive in this form? Where does this negative come from? We basically have these identities, trigonometric identities. When you have sine of minus theta, that is the same thing as minus sine theta. And when you have cos of minus theta, that is the same thing as cos of theta. So if you have a minus sign inside the sine function, that minus comes outside. If you have a minus sign inside the cos function, that disappears. That just gives you cos theta. Now, why is that important? Because in this form, when you have a negative sign here, this negative sign is actually coming from the argument. The actual form was this. So they wrote it in simplified form and asked us to find the modulus and argument from this. The actual form was actually like this. There was a negative inside the argument here, minus 3 pi over 4. There was a negative inside this argument here, minus 3 pi over 4. And in the middle, we had a plus sign here. That was the actual form. However, if you were to simplify this, as I just told you, the minus sign inside the cos, that disappears. So that could be simplified to this. And the minus sign inside the sine function, that comes outside. That's why this becomes negative. So the argument from this would actually be minus 3 pi over 4. The modulus is 3. So in problems like these, now you can just remember, whenever you have a negative sign here, that means the argument is negative, right? You can just remember it like this. Whenever this is negative, that means the argument is negative. You can also think of it like this. Imaginary part is negative, right? Imaginary part is turning out to be negative. If the imaginary part is negative, then that has to be below the x-axis, right? So that's where the argument is negative, right? So you can also remember it like this. So just remember, when you have a negative sign in this form, that negative is going to go with the argument. The argument is going to be negative, right? And that's the logic behind it. Now, in some recent papers, you would see that they want you to find the modulus and argument from power forms like this as well. So you have this power like this, 3 into cos of 2 pi over 5 minus iota into sine of 2 pi over 5. whole raised to power 4. Now, what's the modulus of this complex number and what's the argument of this complex number? Now, if we were to simplify this, simplification of this is quite complicated because we've got a minus b, we've got two terms, and we have to evaluate power 4. We'll have to use binomial expansion for that. That becomes pretty complicated. When you have to evaluate powers, of complex numbers, the best form for you for using there is the re raised to power iota theta form, because evaluating powers becomes very straightforward in that form. There's no plus minus involved here. You can just multiply the power with the existing power. I'll show you how. So this is the complex number, right? 2 pi over 5 cos 2 pi over 5 minus iota sine 2 pi over 5, and we've got 3 outside. What we can do is we can say, look at this complex number. The modulus of this complex number is 3, and the argument of this complex number, because of this negative sign, that's minus 2 pi over 5. That's the argument. So we can write this in re raised to power iota theta form. That's the easiest form to work with when you have to evaluate powers. So write it in this form, re raised to power iota theta. R is 3, theta is negative, so we have minus iota into 2 pi over 5 whole raised to power 4. Now we can evaluate the power 3 raised to power 4, that becomes 81, into e raised to power iota, e raised to power minus iota into 8 pi over 5. So now what's the modulus? The modulus is 81. What about the argument? From this form, the argument appears to be minus 8 pi over 5, right? However, they would have the condition given in the question that the argument has to be between minus pi and plus pi. This is not in that interval. This is outside the interval. Now, where is minus 8 pi over 5 going to be? It's actually going to be like this. This is minus pi, and then you go beyond that. It'll be somewhere here, actually. This is the angle that we're talking about. Now, that's outside the interval. How do you bring that inside the interval? You can go one full circle, 360 degrees, that's 2 pi radians, right? So in order to get back to the same point, by doing one full circle, how do you do that? You either have to do plus 2 pi or minus 2 pi. So you can try that. Try plus 2 pi, minus 2 pi, whichever of them gives you a result that is within that interval. So this is minus 8 pi over 5. This is not in that interval. What you can say is this is negative, right? If you want to bring it inside the interval, what you can do is you can add 2 pi to it, plus 2 pi. And what does that give you? That gives you 2 pi over 5. That's the argument that you have that falls inside the interval. That will be the argument of this complex number. So if your argument is going outside the interval, what you do is you try doing plus minus 2 pi to bring that inside the interval, because 2 pi, that completes one full circle and you get back to the same point. And that will bring your number inside the interval if it is outside the interval right now. So that will be the argument 2 pi over 5. So when you have powers to evaluate like this, you can convert them to this form and then evaluate the powers. Now, there's a theorem that we have here that's not explicitly part of your syllabus, so you don't necessarily have to be able to do it. You can just do this working, but it makes things a lot simpler. If you have cos theta plus iota sine theta whole raised to power n, this actually simplifies to cos of n theta plus iota sine of n theta. If you want, you can use this directly. So when you have a power in this form, cos theta plus iota sine theta whole power n, that power comes down and gets multiplied with the theta. Okay, so if you look at that same example again, the example that we saw earlier, we could do that directly like this as well. We could say, without conversion, 3 raised to power 4, that's 81. And now we've seen what happens in this case. The power will just come and get multiplied with the argument. So 2 pi over 5, that will become 8 pi over 5. And now you could say the modulus is 81. And what about the argument? There's a negative sign here as well, right? The argument is minus 8 pi over 5. And that when you add 2 pi to that, that gives you 2 pi over 5. That's the argument, right? You can do it directly like this as well without even doing that working. If you remember this theorem is called the Moivre's theorem. It's part of the further math syllabus, but you're allowed to use this as well if you want. That will save some time for you. Okay, let's move on. Now, the next thing that you need to know about is properties of products and quotients of complex numbers. What does that mean? When two complex numbers are multiplied, we need to know what happens to their modulus and what happens to their arguments. When two complex numbers are multiplied, you can see this working here, the logic behind it, the background of it, but we get this result that whenever two complex numbers are multiplied, their moduli are multiplied and their arguments are added, right? So let me just show that to you quickly. When you multiply these complex numbers, you see 20 and 4, they will get multiplied and will give you 80. So the modulus is the product of the individual moduli. When you multiply e power iota pi over 6 and e power iota pi over 4, bases are the same, so the powers get added, right? So powers get added, that means the arguments get added. When you multiply two complex numbers, the moduli get multiplied, the arguments get added. When you divide two complex numbers, the moduli get divided and the arguments get subtracted. Okay, so for instance, if you had these two complex numbers and you were asked to figure out what's the argument of z1 into z2, how would you do that? You would just sum their arguments, 2 pi over 3 plus 5 pi over 6. Now you add them up together and that will be the argument of the product. Now in this case, that's turning out to be 3 pi over 2. That's going outside the interval. The interval is this. How do you bring that inside the interval? You can try plus 2 pi or minus 2 pi. Plus 2 pi will make it even bigger. Minus 2 pi, that brings it to minus pi over 2, and that falls in the interval. So we say the argument of that product is minus pi over 2, and that's your final answer. Okay, that's the argument here. So these are properties that we've got that you need to remember. If you have argument of u times v, that will be the same as argument of u plus argument of v, right? Argument of a quotient, that will be argument of the numerator minus the argument of the denominator. For modulus, we've got the same rules. If two modulus are multiplied, we if the two complex numbers are multiplied, their moduli are also multiplied. If two complex numbers are divided, then their modulus are also divided. Arguments, on the other hand, get added and subtracted respectively. Okay, let's have a look at this example. So you'll have to use these properties often when you are asked to prove equations like these. Now, the first part is straightforward here. I've skipped that. In the second part, it says, find WZ. So you've got two complex numbers given, W and Z. They ask you to find WZ first of all, so you can evaluate that, multiply those two complex numbers. That turns out to be 17 plus 17 iota. And then they're saying, by considering arguments, even if they're not said that, you would understand from this equation, that you have to use the properties of arguments. Whenever they say tan inverse of something, and that's part of an equation, or tan of something that's part of an equation in the case of complex numbers, you have to use these properties of arguments, that they get added when numbers are multiplied and so on. So in this case, we've got two numbers multiplied, W and Z, and that's giving us 17 plus 17 iota. W is 5 plus 3 iota, Z is 4 plus iota. Can we find the arguments for all of them? Argument of W, it's in the first quadrant. This is also in the first quadrant. This is also in the first quadrant. All of these are in the first quadrant, right? So their basic angles are going to be the same as their arguments. You can find the argument for each one of them. For the first one, it turns out to be tan inverse of 3 over 5. Now you keep it in this form. Do not convert to decimals, because the equation that they want, they have exact values there. So tan inverse of 3 over 5, we got that there. Find the argument of this as well, tan inverse of 1 over 4, right, for this. And for WZ, it becomes tan inverse of 1. Tan inverse of 1, it actually is an exact value, and that's pi over 4. So now you're getting that the argument of WZ is pi over 4, and the other two arguments are these two. Now you can use that property. You'll clearly write this, that argument of W plus argument of Z, that should equal argument of WZ, right? That's the property that we did earlier. So we could say when these two are added, that should equal pi over 4. And that's the equation that we wanted to prove there. Okay, let's look at another example of this. I'll skip the first couple of parts. They aren't that complicated. In the last part of the sake, by considering the argument of u over u conjugate, prove this thing. Again, you have an equation that has tan inverse in this. You have two complex numbers dividing u and u conjugate. U is this, u conjugate is this. And you've also evaluated u over u conjugate, and that is this. When two complex numbers are divided, what happens to their arguments? Argument of u over u conjugate, that should equal argument of u minus argument of u conjugate, right? So you can find the individual argument, find the argument of u that's in the first quadrant, that is tan inverse of 4 over 3. Find the argument, okay, I'm sorry, argument of u over u conjugate, this is in the first quadrant. Tan alpha equals 4 over 5 over 3 over 5. Find the basic angle, that will be the same as the argument, and that turns out to be tan inverse of 4 over 3 here. Then you find the argument of u, that's also in the first quadrant, so that's tan inverse of 1 over 2. Then you find the argument of 2 minus iota, that's in the fourth quadrant now. Find the basic angle. The basic angle turns out to be tan inverse of 1 over 2. However, since it is in the fourth quadrant, that means it has to be negative. We'll have to go in this direction. The argument would be minus tan inverse of 1 over 2. That will be the argument. Okay, now we've got these three arguments, put them in this equation. Argument of u over u conjugate, that should equal argument of u minus argument of u conjugate. Simplify that and you get that result that they wanted. You can prove that equation like this. Okay, all right. Let's move on. Finding square roots of complex numbers. That's another thing that you have to do. How do you find square roots of complex numbers? Now you need to be able to do them in both x plus y iota form and the other form r e raised to power iota theta form. If you have a complex number in this form and you want to find the square roots of this complex number, how would you do that? Now, this is the standard process that you will use for this. It's generally a 5-mark question, sometimes even 6. You say, let x plus y iota be a square root of that complex number. Then what we're looking for is x plus y iota, that should be equal to 1 minus 2 under root 6 iota power 1 over 2, right? That will be the square root of that. But evaluating power 1 over 2 is very difficult, right? How do you do that? You'll have to use binomial, and that has infinitely many terms. So that does not help. What we do is we say, let's bring this to the other side. So it becomes x plus y iota whole squared. That equals this. You get an equation like this. And now you just solve this equation. How would you do that? You simplify the left-hand side. Simplify the left-hand side. Put iota squared as -1. This is what you get. You've got a real part on the left side. You've got an imaginary part on the left side. Similarly on the right side as well, you've got a real part and an imaginary part. The real part should, if these two complex numbers are equal, the real part should be equal to each other, and the imaginary part should be equal to each other. From that, we get two equations: x squared minus y squared equals 1, and 2xy equals minus 2 under root 6. You solve these two equations simultaneously. When you do that, you'll have to make one variable the subject from the second equation, either y or x. Put that in the other equation. You would get a quartic equation. This is a quartic equation. Now, sometimes in questions, they will say, make a quartic equation to find square roots. Now, do not get confused by that. You just have to follow the same standard process. This equation that you're getting here, this is a quartic equation. Quartic equation is power 4 equation, right? You will automatically get that when you do that. When you solve it simultaneously. Now this is a disguised quadratic then, right? Powers are in the ratio 2:1. One power is double the other. So we can use a substitution to make it a quadratic. Solve that quadratic, put that substitution back at the end, and we get two values of x from this. Remember, x is supposed to be a real number. X is supposed to be a real number, so you ignore the case when you have x square equals -2. You don't write iota there. The value for x that you're getting, the possible values of x that you're getting are plus minus under root 3 from this. Put them in the other equation now, and that will give you the corresponding values of y. And you get 2 square roots from this. 3 under root 3 minus under root 2 iota minus under root 3 plus under root 2 iota. And notice these square roots are negative of each other. They're not conjugate. They're not conjugates. They're negative of each other. For example, just like for real numbers, if 16, if we take square root, if we find square roots of 16, they're plus minus 4. In complex numbers as well, it's going to be plus minus something. So you can see this is one, the other one is just negative of that. Multiply that by negative, you get the other one. These are not conjugates. Okay, they're negative of each other. These are two complex numbers these are two square roots that we were looking for. Now, be careful about the terminologies. This is square root. Root is different. Root means solution of an equation, right? Square root is something totally different. They're not related. Okay. Now, this is very important. You need to know how the square roots of complex numbers are related to each other. So if you have one square root, so let's actually plot them on an Argand diagram. One was under root 3 minus 2 iota. So one square root is here, and the other square root is here, minus under root 3 plus under root 2 iota. Now, what's the relation between them? How are they connected to each other? These square roots are 180 degrees or pi radian rotation of each other about the origin. Square roots are always pi radian rotation of each other about the origin. It's true for real numbers as well. If you have 6 here and -6 there, square roots of 36, for instance, they are pi radian rotation of each other. And it's true for complex numbers as well. Any two square roots of the same complex number, two square roots of the same complex number, they are pi radian rotation of each other. Okay. Now, why is that important? Because you will need to find square roots of the complex numbers, of complex numbers in this form as well. You have to find square roots of complex numbers in this form as well. So sometimes you will get a complex number in this form, and they would want you to find the square roots of that in the same form. Now, one way could be that you convert it to x plus y iota form first, and then you follow all of that process, and then you convert it back to r e raised to power iota theta. But that will be too much work, and this is actually going to be less marks than the other one, because this is going to be easier and quicker. How do you do that in this form? Now, in the previous form, because of that plus or minus in the middle, evaluating power 1/2 was difficult, right? But in this case, in r e raised to power iota theta form, in this case, evaluating powers is not that difficult. So finding square roots could just be done like this directly. We could say we have 4e raised to power minus iota pi over 6. Just take square root on both sides. On the right side, the power is 1/2. So 4 raised to power 1/2, that is 2. E raised to power minus iota pi over 2, pi over 6, you multiply that by 1/2, and that becomes pi over 12. And this is what the square root turns out to be, 2e raised to power minus iota pi over 12. Now that's one square root. What about the other square root? It's not going to be plus minus. Plus minus is not in this form. That's only in Cartesian form. You cannot have a negative sign here because this number outside represents the modulus. Modulus can never be negative, so you would not put minus here for the other square root. The other square root, as we discussed earlier, is supposed to be pi radian rotation of this about the origin. That's why that transformation was important to understand. If you have one square root, that is, for example, here, the other is going to be pi radian rotation on the other side. Now, if it's going to be a rotation, that means the modulus is going to remain the same because the distance from origin, that will remain the same, that will not change. What about the argument? What about the argument? If this argument is minus pi over 12, what is the other argument going to be? How do you go from this to this? It's a pi radian rotation. You could say the other argument is going to be minus pi over 12 plus pi, and that gives you 11 pi over 12. That will be the argument of the other square root. That's 11 pi over 12. So you say the other square root is therefore 2e raised to power iota into 11 pi over 12. And that's it. These are the two square roots that we were looking for. So what you'll do is you'll put a power 1 over 2 there. You'll find one square root from that directly. And then if the argument of that first complex number is negative, of that first square root is negative, you add pi to that to get the other argument, right? So pi radian rotation means you could either do plus pi or minus pi, both will work, right? However, in this case, if you do plus pi, you get something inside the interval. If you do minus pi, you get something outside the interval. So you should be doing plus pi so that you get something inside the interval that's minus pi to pi. So that's what we do. Square roots are pi radian rotation of each other. All you have to do is, let's look at this example now. To find one square root, just put power 1 over 2. And that will give you one square root directly. This is the first one. For the other square root, the modulus will be the same. For the argument, you just do either plus pi or minus pi, whichever gives you an answer inside the given inside the interval from minus pi to pi. In this case, the original argument is positive. If you do plus pi, that will go outside the interval. If you do minus pi, that will be inside the interval. So you do minus pi to get the other argument, and that's the square root. That's the other square root that you were looking for. So this is the standard method that you have. Finding one square root is fairly straightforward. Finding one square root is fairly straightforward. For the other one, what you have to do is the modulus will remain the same. For the argument, if the first argument was positive, you subtract pi from that to get the second argument. If the first argument was negative, you add pi to that to get the second argument. Okay. If the first one was positive, you subtract pi. If the first one was negative, you add pi. Okay. All right. If it is already positive and you add pi to that, that will go outside the interval. Right? That will not be inside the interval. So that would not make sense. You have to be inside this interval, right? From minus pi to pi. So that's how you find the other square root. Now you can see that this method is much quicker, right? Finding square roots in this form is much quicker. So there's a question, could we just convert this complex number to re raised to power iota theta form first? Find the square roots in that form and then convert them back to x plus y iota form. That's possible, but that will be too much work as well. You're doing one conversion and then the other conversion. It's not going to be very helpful. And in some cases, it's not going to be even allowed, because in recent papers, you will see they often say, make a quartic equation and then find the square root. So when they say make a quartic equation, that means that you have to follow this method so that you get that quartic equation and then you solve, then you find those square roots. So sometimes that is going to be necessary. So you have to know both of these methods, okay? One for x plus y iota and the other for re raised to power iota theta form. Let's move on. Okay, next we've got loci. You have loci in complex numbers. Now there are three different types of loci that you would have here. Number one, fixed distance from a point. If you are at a fixed distance from a point, that locus is a circle, right? If you have 4 centimeters from O, for instance, that means it's a circle with radius O, with radius 4 centimeters and center at the point O. If you are at an equal distance from 2 points, that's a perpendicular bisector of those 2 points, right? These are two loci that you have. And the other one, the third one will be of argument. We'll talk about that later. Now, how are these loci related to complex numbers? Let's think about that. Now, before we do that, remember, whenever you draw Argand diagrams, use the same scale on both axes. Use the same scale. Whatever is 1 unit on the horizontal axis, It should be the same thing, that is 1 unit on the vertical axis. Do not use different scales, otherwise your circles are going to look like ovals. Your perpendicular bisectors are not going to be good, and that will not be acceptable. You will draw these diagrams accurately. You will measure on the ruler and mark those points properly, 1 centimeter, 2 centimeter, and so on. Okay. Now, and you will be drawing circles with compass, perpendicular bisectors with compass ideally as well, so that the diagrams are accurate. Okay, now how is loci related to complex numbers? Let's say you've got modulus of z equal to 3. What does that mean? Modulus of z, what does that represent? Modulus represents distance of z from origin. So if distance of z from origin is equal to 3, what we're saying is there's a point z, its distance from origin has to be equal to 3. Distance from a point is fixed. That's a circle. It will be a circle of radius 3 units and center at the point O. Okay. If you have modulus of z less than or equal to 3, what does that mean? Distance of z from origin, that should be less than or equal to 3. So you make a circle and you shade the inner part of the circle. And that's the region that satisfies this condition. Now, what if you have something more complicated like this? Modulus of z minus 2 equal to 4. Now, for this, you need to know a notation. And that is whenever you have z minus something, modulus of z minus something. What does this notation mean? It means distance of z from this point. Okay, this notation means distance of z from this point. Z minus something modulus of that. Okay. So for example, if you have z minus 2 modulus, that equals 4, what that means is distance of z from the point 2, that is equal to 4. So what's the locus going to be? It's going to be a circle with this point as the center and this as the radius of the circle. Okay, so you draw a circle like this with 2 as the center and radius equal to 4. If you have z plus 2 minus 3 iota, now this is not the standard form. So the first thing you have to do is you always have to convert it to the standard form. What's the standard form? Z minus something. Okay, so you have to convert it to that form first of all. You take minus common from these two terms, and that becomes this. And now this is the center of the circle, and this is the radius of the circle, right? Minus 2 plus 3 iota is the center, and then 2 is the radius. You draw that circle there. Now, from this, we actually get a form for equation of a circle as well. Sometimes they may ask you, I have seen a couple of questions like this in past papers, where they ask you to write down the equation of a circle in this form. Okay, so this is another. So one form is what you've done in coordinate geometry before: x minus a whole squared plus y minus b whole squared equals r squared. But in complex numbers on an Argand diagram, we can use this form for equation of a circle as well: z minus some expression, z minus that point, modulus of that equals r. The number on the right side, that represents the radius, and this represents the center. Okay, you can write it. So this is equation of a circle. This is equation of a circle with minus 2 plus 3 iota as the center and 2 as the radius. What if you have this? Z minus 1 plus 2 iota, modulus of that equals modulus of z plus 3. Now, first of all, you have to convert it to standard form. Before that, you cannot do anything. The first thing is to convert it to standard form, z minus something. Now, it looks like you have z minus something here, but no, you have to take minus common outside. Take minus common, that leaves you with 1 minus 2 iota inside. On the right side, you have z plus 3, right? That is z minus minus 3. So now this is the point that we're talking about. This is the point that we're talking about. We're saying z is such that its distance from 1 minus 2 iota is equal to the distance of z from this point. Now we're talking about 2 points. We're not talking about 1 point anymore. We're talking about distance from 2 points. Distance from 2 points is equal. What kind of locus is that? That's a perpendicular bisector. What we do is we mark these 2 points. One point is minus 3 and the other point is 1 minus 2 iota. We mark those 2 points. And then the locus is going to be the perpendicular bisector of those 2 points. It has to pass through the midpoint of the line joining those 2 points and should be perpendicular to that line. Okay, perpendicular bisector. You can use a compass for this. If you're not using a compass, still draw it as accurately as possible. You can mark the midpoint and then make a right angle here using a set square or a ruler. Make sure that the angle is 90 degrees. Okay. It has to be reasonably accurate. That's important. Now, you could have inequality here as well. Again, you convert it to standard form, and then you're saying distance of z from this point is greater than distance of z from this point. What does that mean? Which point is z closer to? Z is the distance is more from this point and less from this point. So that means the point is closer to -3. The point z is closer to -3. So what you would do in this case would be you would draw a perpendicular bisector and shade the side on which you have the number -3. Shade that side on which you have -3. Okay. It's not going to be that when you have a greater than sign, you shade the upper region, you have minus and you shade the lower region. No. You have to think about which point you are closer to. Which point you're closer to. So you're closer to -3. So you shade this side on which you have -3, you shade that side. Okay. Now it's a strict inequality. You could draw a dotted line here as well because the points on the line, they are not included. However, in A-levels, they don't deduct marks for that. If you have greater than or greater than equal to, both of them are normally dealt with the same way. It doesn't make any difference. What about argument? So you have, this is another locus that you have. Argument of z equals 2 pi over 3. This is the third type of locus that you can have. Z is a number such that its argument is 2 pi over 3. Now, where is argument going to be measured from? From the positive x-axis, right? That's where you measure argument from. Now, what's the argument? This is 2 pi over 3. So from that point, from that line, you measure 2.2 pi over 3, and you draw a line like this. That is going to be the locus of this point, right? From the origin, you have a line in this direction. But here as well, you could have z minus something, z plus something. Now, in this case, how do you understand this? This is the standard notation that we've got. Argument of z minus some expression. We would say this means argument of z from the horizontal line drawn to the right side of that point. So we will be measuring the angle from that point. If you draw a line on that point, the angle will be measured from that point. For instance, if you have argument of z minus 2 iota, and that is equal to minus pi over 6. What do we do for this? What's the point that we're talking about? We're talking about 2 iota. Where is 2 iota? This is the point 2 iota. We draw a horizontal line, this yellow line. You don't necessarily have to draw this. You can draw a dotted line like this, like I've drawn here. Draw a dotted line. The argument has to be, the angle has to be measured from this line now. What's the angle? That's minus pi over 6. Minus pi over 6 is on this side. It's you go clockwise. Pi over 6 is 30 degrees. So you roughly draw that angle. You can ideally use a protector for this. Or you can do it without that as well. That's going to be acceptable. But I would recommend still that you do it using a protector because a lot of times you have a next part to this question in which you have to do some calculation. And that becomes much simpler if you've drawn the diagram accurately. It makes it easier for you to understand what's happening in that situation. So I would recommend that you draw it accurately, especially if there's a calculation part after this. If they have something like this, argument of z plus 2, that is between minus 2 pi over 3 and pi over 6. First of all, you convert it to standard form. This is z plus 2. You say this is z minus minus 2. So now we're talking about the point minus 2. That's our point of reference. Mark that point minus 2. This is the point. And this is the point minus 2. So the argument is going to be measured from that point. So this yellow line that you see, we're measuring argument from that. One argument is minus 2 pi over 3, that's minus 120 degrees. And that is in this direction here. And the other is pi over 6, that's in this direction, 30 degrees. And then they're saying the argument is between these two values, So you shade this region like this, right? Like I've done here, this green part, that's the part that satisfies both of these conditions. This is another example. If you have argument of z minus 2 plus 3 iota, again, you convert it to standard form. The reference point, the point of reference is 2 minus 3 iota. So argument will be measured from that point. Now, when you have an angle of pi over 4, or 3 pi over 4, or minus pi over 4, these are very important to be drawn accurately. What's pi over 4 angle? Pi over 4 angle is 45 degrees. 45 degrees. When you have a 45-degree line, it always has a gradient of 1, right? It has a gradient of 1. And whatever distance you're traveling horizontally, it should be the same distance that you travel vertically, right? Because it's an isosceles triangle that you get like this. So opposites, these sides have to be equal to each other. So with a pi over 4 angle, whatever distance it is that you're traveling in one direction, it should be the same distance that you travel in the other direction, as in horizontal direction, vertical direction. For example, in this particular case, you're measuring argument from 2 minus 3 iota. Let's mark that point here. 2 minus 3 iota, that's this point here. What's the argument? Pi over 4. Pi over 4, that's the argument. Now, you would draw a line here like this. Measure pi over 4, 45 degrees, right? Now, this line that you draw, it must pass through this point 5. It should not be to the right of 5, to the left of 5. It has to pass through 5. Why? Because the vertical distance from this point to the x-axis, how much is that? That's 3 units. So if you're going 3 units up, you have to go 3 units right. So that means you have to pass through this point. If it's not passing through point 5, that will be wrong. Okay. And if there's a calculation part after this, it's very unlikely that you'll be able to do that. Okay. So for pi over 4 lines, you have to be very careful. Similarly, minus pi over 4 will be 45 degrees in this direction. 3 pi over 4 will be 45 degrees in this direction. So whatever is the distance you are traveling in one direction, it should be the same distance that you're traveling in the other direction. That's important for pi over 4 degree lines. Yes, that's what I said earlier as well. You have to plot the points, measuring them using a ruler, as in you have to mark these points on these axes with measurement, right? You can say 1 centimeter for 1 unit. Place a ruler and mark the points using that. Okay, that's important. Otherwise, if the diagram is not accurate, the calculation part becomes even more difficult. Okay, now based on these loci, you would have to do some calculations sometimes. They will ask you to find greatest value of modulus of z, least value of modulus of z. Modulus represents distance from something, right? Now, there are two types of loci that you have. One is a line and the other is a circle, right? Now, when you have to find the least distance from a line, that distance is always perpendicular distance. So for example, let's say they have this locus that's a line, and they say, find the least value of modulus for points on this locus. Now, let's say this is the origin. What's the least modulus going to be? The shortest distance from origin to that line, that's always perpendicular distance, right? Shortest distance from a point to a line, that's always perpendicular distance. What if the locus was a circle? So let's say the point z could be anywhere on the circumference of the circle, and what you want to do is you want to figure out the shortest distance from a point to the circumference of the circle. So for example, they might ask you, what's the least value of modulus? How do you find that? Least value of modulus, again, is going to come when you have a line that makes 90 degrees with the circumference, right? What would that line be? Normal to the circle, right? If you were to extend that, that will actually pass through the center of the circle. So shortest distance is going to be, you draw a line from that point to the center of the circle, where that line cuts the circumference. Until that point, this distance is the shortest distance. How do you find that? You would have the point O, you have the point R, as point C. You can find the distance between O and C, subtract from that the radius, and that will give you that shortest distance. What about this largest possible distance, the greatest possible distance from origin to a point on the circumference. For that, what you would do would be you would say, start from here. What's the greatest distance? You can go here, go to the other side, and go all the way on the other side like this, such that you pass through the center of the circle and then cut the circumference on the other side. That will give you the greatest distance from a point to the circumference of the circle, right? That's the greatest distance that you have in this case. Passing through the center and going and cutting the circumference on the other side. This distance is OC plus R, right? That's the greatest distance. So when they ask you for greatest modulus, that's something that you may have to use sometimes as well. And then what about arguments? For example, let's say you have a point O here, and you want to find the locus is a circle like this. Okay. You want to find the least argument for points on this circumference. What's the least argument going to be? Argument is measured from the x-axis, right? So this is where the argument is going to be measured from a horizontal line, right? You keep increasing this angle. What's the first time that you touch the circumference? That's this point here, such that you make a tangent at this point. This angle is going to be the least argument. What about the greatest argument? That would be that you make a line like this from that point again. You keep increasing. How do you maximize this angle? When the line touches the circle on the other side, that is when the angle is going to be maximized. It's called that angle beta. This is the maximum argument, the greatest possible argument that you can have here. Okay, and how would you find these values now? When you have two tangents, remember that circle property, you would always break it down like this. We'll make a line from that point to the center of the circle, so that you get two right angle triangles like this. And then using those right angle triangles, you can find these arguments somehow. Using those right angle triangles, you would have some lengths, like you'll have radius there, you'll have this distance from O to C. You can use that to find some angles. Similarly, you'll have the point C, you'll have the point O. You can also make a right angle triangle like this, and that will give you some lengths as well, some angles as well. Okay, so you can use those properties to find this. Kite property, you can call it that. It's that circle property in which you have two tangents coming from outside the circle, right? You get a kite like this, you break it in the middle, you get two congruent triangles. You can use those triangles to figure out the angle, right? That depends on the question. So these are all the different concepts that you have in complex numbers. Now let's have a look at some questions quickly. On complex numbers, I'll go through them quickly. You have the notes with you. You can go through them in your own time as well later on. Now, when you draw loci, a lot of times they give you two conditions at the same time. For example, here, they're saying modulus of z is less than modulus of z minus 2, and argument of z minus u is between 0 and pi over 4. Now, in this case, there was a first part to this question in which u was given to be minus 2 plus iota, right? U is minus 2 plus iota. That's given in the question. Okay, that's not something that we're assuming. That is given in the question statement. Okay, now, how do we draw these loci? Modulus of z is less than modulus of z minus 2. We can think of modulus of z as modulus of z minus 0, right? So we're talking about distance from origin. Distance of z from the origin, that is less than the distance of z from 2. We're talking about distance from 2 points. When we talk about distance from 2 points, the locus that we draw is a perpendicular bisector. So we'll be drawing a perpendicular bisector here. For those 2 points, one is 0 and the other is 2. What's the perpendicular bisector going to be? It's going to be a vertical line at 1, right? That's the perpendicular bisector. And now the condition is distance from 0 is less as compared to distance from 2. Which side should we shade? It's closer to 0 because distance from 0 is less, right? And it's far away from 2. So the side on which you have 0, that is the side that's going to be shaded. So for this vertical line, 0 is on the left side. So you shade the left side because of that. right? So left side is what you would consider. But that's not the only condition that you have. You have another condition as well, and that is that the argument of z minus u, that is between 0 and pi over 4, we are given the complex number u is minus 2 plus iota. We can mark that point here. This is the point minus 2 plus iota. So argument will be measured from that point. Minus 2 plus iota, at that point, we could draw a horizontal line and measure the argument from there. One is 0. So we have a line at 0 here like this. And the other is pi over 4. Now, again, as I said, you have to be careful about pi over 4 angles, 45-degree angles. Whatever distance you're traveling horizontally, it should be the same distance. It should be the same distance that you're traveling vertically. Okay, so if you're traveling 2 units horizontally, you have to be traveling 2 units vertically. So this line has to pass through 3 here. That's necessary. Okay, so that's the other line. And you have to be between these two lines. So between the two lines and to the left of that vertical line, what's that region? That's this green shaded region that you have. That satisfies all of those conditions. That is what you would shade there. It does not matter if the line is shaded or if the line is dashed or not. In A levels, they do not deduct any marks for this. Okay. You could also remember it like this: when you have an inequality, shade the side towards which the inequality is put. No, not the side. Look at the side to look at the point to which the inequality is pointing. So this is an inequality, right? It's a less than sign. The pointed side is towards 0. So the inequality is pointing towards 0. So you will shade the side that has 0. Okay. So that's not logical, but as in, that's just a way to remember. I told you the logic behind that, as in it has to be close to 0. But if you just want to, not think much, you can say whichever point the inequality is pointing towards, you will shade that side, right? So it's pointing towards 0. So whichever side 0 is on, that will be the side that you shade. Okay. All right, let's move on. This is another example. Again, you're given two inequalities here. Perpendicular bisector of 1 and iota, you would draw that. And then you have to be closer to 1, right? 1 and iota. So 1.1 is this, iota is this. Perpendicular bisector of these two is going to be the y equals x line, right? Because this looks like this. It's a -1 gradient. When you draw perpendicular bisector of that, that will be the line y equals x, a 45-degree line like this. Okay. The other is modulus of z minus u is less than or equal to 1. So distance of z from a point that is less than or equal to 1. We're talking about 1 point here. So that's a circle. Center of the circle is going to be u, which is 2 plus 2 iota, and the radius is 1. So you draw that circle. You have to be inside that circle and towards the point 1. So inside the circle towards the point 1, that gives you this semicircle. When you draw this accurately, you'll get this semicircle. Okay, that's what you shade there. And then they're saying use a diagram to calculate the value of modulus of z for the point in this region for which the argument of z is least. Now, what does that mean? We want to find out modulus of z for the point for which argument of z is least. Now, where is the argument least? You measure argument from the origin, right? Where is the argument least? Where is the argument least? That's going to be when you have a tangent here at this point A that I've marked, right? This point A is what we're talking about. This is the point at which the argument is least. At this point now, we have to find the modulus. How do you do that? You can make a right angle triangle. Whenever you have a tangent, you draw a right angle triangle like this. And using that right angle triangle, you can find whatever is missing. So the radius is 1, you know this side is 1. And you know the distance between the origin and the center. You can find that, right? Using distance formula. So you find that distance turns out to be square root of 8. Use Pythagoras to find the length of OA and that turns out to be under root 7, you say that's the value of the modulus of z at that particular point, right? So you have to do these calculations. Based on this locus, okay? They have to be passing through the points through which they have to be passing, right? For example, if you draw a circle of radius 1 and center is at 2, 2, you have to make sure that on the left side it goes up to 1, on the right side it goes up to 3 here, below it goes up to 1, up it goes up to 3, right? So you have to make sure that is happening. If you have a pi over 4 line, you have to make sure, as I said, it's traveling the same distance horizontally and vertically. Okay. All right, let's move on. This is another example. You can have a look at this. Modulus of z less than equal to 3. That's inside the circle. Real part of z is greater than equal to minus 2. What does that mean? Real part is plotted on the horizontal axis. So if real part of z is greater than equal to minus 2, what that means is horizontal axis is x, right? So we're talking about this. X is greater than equal to minus 2. So you draw the line x equals 2. What's that line? That's going to be a vertical line. This line here. This represents when real part of z is equal to minus 2. Greater than equal to minus 2, that means you have to be to the right of this. And then you have this argument condition as well. You shade the region that satisfies all of those conditions. You can see that here. Okay, let's move on. Now, this is a fairly tricky one. Look at the second diagram, second question, the second part of this question. Argument of z minus 2 iota, that is equal to pi over 6. And modulus of z minus 3 is modulus of z minus 3 iota. They intersect at the point P. So you draw those two loci, and they intersect at this point P. And they want you to represent the number P in the form r e raised to power iota theta, such that you have the exact value of theta. R can be in decimals, but the value of theta has to be exact. How do we do that? So when we draw these loci, for the two loci that we have are, you have this 3 here, the other is 3 iota. You mark those 2 points. You've got this point 3 here, this point 3 iota here. When you draw perpendicular bisector of this, it's going to be the y equals x line. It has to pass through the origin. If you don't draw this accurately, you will not be able to do the second part. So when you draw perpendicular bisector of this, it passes through the midpoint and passes through the origin because of it being perpendicular to that. And then this is one locus that you have. The other is that the argument of z from 2 iota, what's the point 2 iota? This is the point 2 iota. From this point, the argument is supposed to be pi over 6. You draw a 30 degrees line from that. Now that does not have to be very accurate, 30 degrees line. That will be approximate, and that's okay. So this angle is pi over 6. Okay. And now we are supposed to represent this number P in the form r e raised to power iota theta. How can we do that? We have to find the modulus of this number and the argument of this number. What's the modulus going to be? Let's figure out the angles. Do we know the angle? Since we knew that it's perpendicular bisector of this original line had an angle of had a gradient of -1. Its negative reciprocal would be a gradient of 1. Gradient of 1 lines have an angle of pi over 4. So we know that this angle is pi over 4, right? It's y equals x line, as we said. The angle is 45 degrees or pi over 4. So the argument has to be pi over 4. We know that, right? What about the modulus? How do you find the distance OP? You could think of the angles like this. You could say, if this is pi over 6, this is 90 degrees, or pi over 2. Pi over 2 plus pi over 6, that total angle becomes 2 pi over 3. Sorry about that. That total angle becomes 2 pi over 3. This angle at the bottom is pi over 4. You can find the third angle as well. You've got 3 angles in that triangle, and you know one side, this side is 2 units. So you can find the side OP using sine rule, and that gives you the result. That's what you were looking for. That's the modulus of the point P. And then you can write that in r e raised to power iota theta form. No, you can't do this from the graph. You have to do this by calculation. You cannot measure from the graph or mark or take the point from the graph. That's not allowed. It would not be so accurate in any case. 3 significant figures, you can't get an answer to 3 significant figures from a graph that does not even have a grid, right? So you can't do that. Okay, now the first two parts of this question are really straightforward. You have to find modulus and argument of them, and then in the last part you see they're saying the roots that we got in the first part, you have to show that they also satisfy this equation. Z raised to power 6 equals minus 64. How do we do this? Evaluating such big powers of Z is going to be pretty long if you do this power 6, right? You have to use binomial expansion, and that becomes fairly complicated then. Fairly long. You have iota raised to power 5, iota raised to power 6, right? So how do you deal with problems like these? Remember I said evaluating powers is simpler in r e raised to power iota theta form. They made you find the modulus and argument in the second part for both of those roots. You can write those roots in this form: r e raised to power iota theta form, 2 e raised to power iota power 6, and 2 e raised to power minus iota power 6. You write those numbers in this form, and then you input these numbers in this equation to see if they satisfy or not. So convert them to r e raised to power iota theta form, and then you input them in that equation, this equation. Now simplify this, evaluate the power. When you evaluate the power, you end up getting this. Now, how do you know that this is equal to minus 64? Now you go back to the cos theta plus iota sine theta form from this, right? R into cos theta plus iota sine theta form. Simplify that, put this on your calculator, and sine of 5 pi is 0. Cos of 5 pi is minus 1, and that gives you minus 64 equals minus 64. Do exactly the same thing for the other root as well. Convert it to r e raised to power iota theta form, input that in that, and then you go back to the other form to simplify that, and that proves that this satisfies the other equation, this equation as well, right? So when you have large powers, like big powers like this to evaluate, using the r e raised to power iota theta form is much more efficient. Okay, this is another example. You can have a look at this. Sometimes you have to use trigonometric identities and complex numbers as well. Very rare, but you may end up having to do that sometimes. You can have a look at this working. It's just trigonometry. Okay, so W in the second part, they said that W has modulus 1 and argument 2 theta. So that W minus 1 over W plus 1 is iota tan theta. Now, since we have to say that I have to convert it to tan theta, that means trigonometry is involved. So we write it in the r cos theta plus iota sine theta form, right? And that becomes this. Then we just input that in this form and simplify that, use the double angle identity, simplify everything, and try to, get to that form that we want, iota tan theta, using trigonometry. You can have a look at this working. I'll move on after this. Okay, this step is important. So at one point, I got this tan theta into this whole thing. And now the final result that we want, that has iota tan theta. So they want an iota in the numerator, right? To make that process quicker, what I did here was I said Okay, I want iota tan theta in the numerator. So let's multiply and divide by iota. Iota is just a number, right? So we can multiply and divide by iota at this step. This is what we want, and everything else we want to just cancel out somehow, right? So you simplify the denominator, and that gives you this, and then you get some cancellation that happens there. Okay, let's move on. You can have a look at this working. This is another example. You draw this locus. In fact, this is the other way out. So in this case, what happens is they give you a shaded region on the diagram. This is part of the question. They give you this part shaded like this. And then they say find two inequalities in terms of z that define the shaded region. How do you do that? How do you write down two inequalities yourself? How do we think about this? We have a circle. What's the center of the circle? -2 and 1. In complex number form, we can say that's -2 plus iota, right? That's the center. What's the radius of the circle? That's 3 units. So we have to be inside the circle. So we could write down the equation of the circle like this: modulus of z minus -2 plus iota. That should be less than or equal to 3 because we have to be inside the circle. That's one inequality that we get. We put an equal to sign here because they're saying the boundaries of the region are included in the shaded region. So we put an equal to sign there as well. And then what else? The shaded part is below this line. This line that we've got, the shaded part is below that line. Now, what is this line? It's y equal -1 line. Now, in Argand diagram on the vertical axis, we've got the imaginary part, right? So we can say that's imaginary part of z equal to -1. We have to be below this line. So we say imaginary part of z is less than or equal to -1. Sometimes we have to do this as well, that they give you uh, a shaded part themselves, and you have to write down the inequalities from that. So you have to write down the inequalities. So in this case, we had modulus of z. This is the standard format, z minus some expression, modulus of that is equal to r. That's the standard form of a circle that we discussed earlier, right? So center is -2 plus iota. We put -2 plus iota there. Radius is 3. We put 3 there. But instead of being equal, we say it's inside the circle shaded part. So we put a less than equal to 3. We put less than equal to sign there because we have to be inside the circle. All right. Hope that makes sense. And then for the other one, we got imaginary part of z less than or equal to -1, right? Then they say find the greatest value of modulus of z for points in this region. Now, what about the greatest value of modulus of z? Modulus of z means distance from origin. So we start from here. What's the greatest distance in the shaded part? What's the greatest distance in the shaded part from the origin? Is this the greatest? No. You can keep going further and further until you touch the touch the shaded part on that extreme end, like that. That's the greatest value of modulus. How do you find that? How do you find this distance? That's quite complicated. Now, a quicker way of doing such things, if you can't think of something more efficient, you can use the equation of circle form from paper 1, if you remember, to find this point. And then you can find the distance easily after that. How do you find this point? You know the y coordinate. The y coordinate is -1 at this point. Do you know the equation of the circle in coordinate geometry form? X minus a whole squared plus y minus b whole squared equals r squared. Sometimes that becomes very helpful in these first sense. Center is 2, -2, 1, radius is 3. We could say the equation of the circle becomes this. Now, when y is equal to -1, find the value for x that you get. The value for x that I get is this, -4.236. That means that's the x coordinate of that point. So that point that we're talking about is -4.236 and -1. Find the distance of this point from the origin. Use Pythagoras or the distance formula, and that gives the distance. That's 4.35, and that's what we were looking for. So sometimes when you're looking for the point of intersection of a circle in an Argand diagram, it helps to use that coordinate geometry equation of circle form to find that point, and that makes things easier. Okay, it'll take a few steps, but it's not that long that it takes. Just a few steps, easy steps, rather than spending a lot of time thinking about another more efficient method. You will spend a lot of time thinking there. Just use that equation of circle form to find that point, and then it becomes very straightforward after that. And this is another example: cos of pi over 7 plus iota sine of pi over 7 whole raised to power 4 divided by this. We need to find the exact value of argument of this complex number. Two complex numbers are divided. When two complex numbers are divided, what happens to their arguments? What happens to their when two complex numbers are divided, what happens to their arguments? Their arguments are subtracted, right? Now, what are the individual arguments? What are the individual arguments? Argument of the numerator. What's that? We can use the De Moivre's theorem that I told you about. Multiply 4 with this. Argument of the numerator is 4 pi over 7. Right? That's the argument of the numerator. What about the denominator? We have a negative sign here. That means it's minus pi over 7. You subtract from 4 pi over 7 minus pi over 7, and that gives you 5 pi over 7. That's the argument of u. That's what you were looking for. Alternatively, you could convert it to r e raised to power iota theta form, and then evaluate that power. That's also not that difficult, right? Evaluate power 4, that gives you the argument, that's 4 pi over 7. For the denominator, it's obvious as the argument is minus pi over 7. You find their difference and you get the result from that. Okay, I'll answer questions in a few minutes once we're done with that. Done with it. I think there are only a few examples left. Now, this is something that they ask about a lot. If you have a complex number u and its conjugate, a complex number and its conjugate, they're always reflection of each other in the x-axis, right? Because the imaginary part is opposite. So if you have one point here, the other point will be on the other side. It's always reflection in the x-axis, or you can say reflection in the real axis. So if argument of u in this case was 5 pi over 7, that's in the second quadrant here, right? 5 pi over 7, that's greater than 90 degrees, greater than pi over 2. That's 5 pi over 7. What about the argument of u conjugate? That will be here. On the negative side, that becomes minus 5 pi over 7. That's the argument of u conjugate, and its reflection in x-axis. Okay, this is a recent question that you can have a look at. Z equals 1 plus y iota. You have to find 1 over z first of all. That's just using conjugates. And the second part, they say, show that a minus 1 over 2 whole squared plus b squared is equal to 1 over 4. Now, what does that mean? This form that we found in the first part, that was a plus b iota. So this was a and this was b. No, this was not b. This whole thing was b, right? Including the negative sign. They're saying show that this is equal to 1 over 4. The left-hand side is equal to 1 over 4. So what we can do is we can just, input values in this, simplify everything. It requires some simplification, and eventually things get cancelled out, and you get 1 over 4 as the result. That's what you have to prove in this case. That the left-hand side equals 1 over 4. Now you have this locus to draw. That's pretty straightforward. Now, this is important. In the previous part, what we've done is you have drawn this locus that satisfies these two equations. Real part of z is equal to 1, and the modulus of z minus 1 over 2, that is equal to 1 over 2. This is a circle, radius 1 over 2, center at 1 over 2. Real part of z1, that's this vertical line. Now, these are the two loci that are given by these two equations. Now they're saying the complex number z is such that there's a complex number z such that the real part of z is equal to 1. That's this condition, right? Use your answer to part B to give a geometrical description of the locus of 1 over z. Now, how do we think about this? In the second part, we have shown that a minus 1 over 2 whole squared plus b squared, that is equal to 1 over 4, right? That's what we have shown in the first part and in the second part. Now, what does this look like? A minus 1 over 2 whole squared plus b squared, that equals 1 over 4. Does that form look familiar? That's the form for equation of a circle, right? X minus a whole squared plus y minus b whole squared equals r squared. So it's very similar to that. A represented the horizontal axis, A represented the real part here, B represented the imaginary part here. So this is the form of equation of a circle, such that the center of the circle is 1 over 2 and 0. And radius is what? Radius is square root of this. That's 1 over 2. So in the second part, the form that we were given, if we compare that with the standard circle equation form, the variables here are a and b, not x and y. If we compare with that, we actually get that it's a circle with radius 1 over 2 and its center at the point 1 over 2 and 0. That's actually the locus that you have drawn in the previous part, right? That's this circle. That's the locus of 1 over z that follows that form of equation of a circle. So sometimes we get these weird problems in some recent papers. This is another very different kind of locus problem that you find in a recent paper. And the complex number z satisfies modulus of z equals to an argument of z between 0 and pi over 4. Use the Argand diagram below to sketch the locus of the points representing z. Now, where could z be? Modulus of z is equal to 2. So it has to be on the circumference of the circle, right? Center 0 and modulus 2. And the argument is between 0 and pi over 4. Now it has to be on the circumference. The argument is between 0 and pi over 4. That means 0 and 45 degrees. So we draw a 45-degree line here, pi over 4 gradient line, and a 0 gradient line. Now, what's the region that satisfies both of those conditions? You have to be on the circumference of the circle, and the argument has to be between 0 and pi over 4. That's this yellow region here. That's what satisfies both of those conditions. This is what represents z. On the same diagram, sketch the locus of the points representing z squared. Now, what is z squared going to be? When you square a complex number, that means it's z times z, right? Modulus will get multiplied, so that will be 2 times 2, then that's 4. What about the argument? Arguments get added. So argument of z squared is going to be 2 times argument of z. So argument of z squared therefore would be between 0, 0 into 2 is still 0, and pi over 2, because pi over 4 times 2 is pi over 2. So the other one is when you have a circle of radius 4 units, a circle of radius 4, that's this outer circle, and the angle, the argument is between 0 and pi over 2, 0 and this line pi over 2. Which region satisfies that condition is this region, right? This is where both of these conditions are satisfied, this highlighted part. Now you can either get rid of the rest of it or make sure that you clearly show that this is the only part, the shaded part, that satisfies the condition. You can also just erase the rest of it because that's not needed. But erase the rest of it like this if you wanted, or at least just shade that part that satisfies the condition. Okay. Why is the argument of z squared until I think my iPad also wants to sleep now. I'm not sure what's happening to it. बस का जो है क्या हो गया? Okay. Okay, so this is what we had, right? Argument of z squared would be product of argument of z squared would be the sum of the argument of z, right? Argument of z into z is argument of z plus argument of z. So that's 2 times argument of z. Now, if argument of z was between 0 and pi over 4, what about argument of z squared? Then we multiply this interval by 2. 0 times 2 remains 0. Pi over 4 times 2 becomes pi over 2. So its argument becomes pi over 2 for that reason. Okay. You can have a look at this example. Express z squared in this form. You can see that working. And the second part, they're saying the complex number w is such that z squared w is real. Now, when they say something is real, that means it has to lie on the horizontal axis, right? That's what it means. And z squared over w modulus of that is equal to 12. Find the two possible values of w, giving an answer in the form r e raised to power iota alpha, where r is greater than 0 and alpha is between minus pi and plus pi. Now, how do you find w from this? Now, first of all, z squared w is real. That's what they're saying, right? We could say w is equal to r e raised to power iota alpha like this. Evaluate z squared w from that. We know the value for z squared already from the first part. Z squared w turns out to be this. Okay. Now they're saying it's real. Okay, it's real. That means it has to be on the horizontal axis. If it is on the horizontal axis, then that means that the argument would either be 0 or it would be pi, right? It either be on the right side or on the left side. So argument can either be 0 or pi. These are the only two possibilities that we have. And they're also saying that the modulus of z squared over w, that is equal to 12. Now, if using the modulus, we could actually find the modulus of w easily. That turns out to be 1 over 3, right? Because we know the modulus of z squared already. And from that, we can get the modulus of w. That turns out to be 1 over 3. What about the argument? The argument, as we said, could either be 0 if it's on the right side on the real axis, or pi if it's on the left side, right? So we could say this argument minus pi over 3 plus alpha could either be equal to 0 or it could be equal to pi. And that gives us the two possible values of the argument. One is pi over 3, the other is minus 2 pi over 3. And then you can say the complex number w therefore is either 1 over 3 into e raised to power iota pi over 3 or 1 over 3 into e raised to power minus iota 2 pi over 3. It's quite tricky the first time you look at it. And have a look at this working again and understand what's going on. Since it said that it's real, it had to be on the horizontal axis, right? So that's why the argument had to be either 0 or pi. Okay, all right. This is another loci problem. You can look at the first part. That's pretty straightforward. In the second part, they say find the greatest value of argument of z for points in this region. Where will the greatest value be? When you touch the circle at the highest point here, right? That's where the greatest and the argument would be greatest. And now we have to find this argument. How do you do that? Again, if you can find this point somehow, that will simplify things for you. Now, there might be a more efficient way of doing this as well, yes, but that will require some thinking as well, right? So you can directly find that point using the equation of circle form, right? The equation of the circle, you know that the, you know what? you know that this point is x equals 5 because of that line that you have there. What line do you have there? Do you have that line? Yeah, perpendicular bisector of 0 and 10 that is passing through 5. So the x coordinate is known. You put that, you get the corresponding y coordinate that turns out to be this, and then you can find the angle based on that, right? So this equation of circle often becomes is helpful to find that point where the circle is intersecting with some line, the equation of circle from coordinate geometry, and then you can do the calculations after that. This is another example. In the first two parts are polynomials. Okay, this is another thing that they often ask you to do in complex numbers. Show that some number is a root of an equation, and that's a complex number, right? How do we do that? How do we show this? It has z cube as well, right? You would evaluate z square and z cube on the side first of all. So this is z, evaluate z square from that first. And once you have z squared, then you can multiply z squared with z again to find z cube. So you have z cube and z square. Then you input them there, and the iotas will get cancelled out eventually, and you'll get 0 at the end, right? So you have to show this working. Without working, you'll not get marks. You have to show this working, okay? Now, this is important. In this part B, they told you that this is one root of this equation, -1 plus 2 under root 6 iota. And then they're saying in the next part, the complex numbers z, which are roots of this equation, p of z squared equal to 0. Now, how do you find those complex numbers? First of all, we know this is one root, -1 plus 2 under root 6 iota. This is another root. They told us that x equals -3 is also a root. If x plus 3 is a factor, x equals -3 is a root. So we know another root. Since all coefficients are real here, the conjugate of this would also be a root. So we know the three roots of the previous equation. When p of z is equal to 0, the three roots that we have are these, this, and this. Okay. They're saying find the roots of this equation, p of z squared equal to 0. For that equation, that would mean we have z squared equal to this, or z squared equal to the other complex number, or z squared equals -3. So instead of z being equal to those solutions, we have z squared equal to each one of them. And then we find the possible values of z from this. How do you do that? If z squared is equal to this, we have to find the square roots of this complex number. How do you do that? Using the x plus y iota method. X plus y iota whole squared. Apply that whole process. You get the two square roots, and they give you this. These are two roots. Do the same thing for the other complex root. You say z squared equals that. Again, apply that process for finding square roots of that complex number, and you get two other square roots. These are two more solutions. And then you have z squared equals -3. This is easier. Take square root. When you take square root, you have plus minus. That becomes plus minus under root 3 iota. So you get 6 solutions in total for this. You had solutions of p of z equal to 0. They wanted solutions of p of z squared equal to 0. So whatever were the solution for z, we said z squared should equal them as well, and find the corresponding values of z from that then. Okay. That's another thing that can happen. Now we have this complex number. We know the argument of this complex number is -5/4. First of all, they say find the value of a and hence express z in the form x plus y iota. How do you find the value for a? First of all, you can write this complex number in x plus y iota form. Okay. As in split it into two. You have iota in the denominator, right? To be able to find the argument, you need x plus y iota form. You need the real part separate, the imaginary part separate. So you multiply and divide by the conjugate, and that gives you this form. Now, This is the real part, this is the imaginary part, including the negative sign, right? Now they're saying that the argument is minus 5/4. That means it has to be in the fourth quadrant here. Minus 5, minus 5/4. What's the basic angle that we get from that? The basic angle is 5/4. So now we can apply that formula. We can say tan of 5/4, that should equal the imaginary part divided by the real part. And then we get an equation from that. Solve that equation to find the value for a. We're getting two values of a here. They said that a is supposed to be an integer, so we only consider the integer value. Put that value of a back in this, and that gives you the complex number in x plus y iota form. So sometimes they will give you the argument of a complex number like this, and there will be something missing. This is how you would approach that. You will separate out the real part and imaginary part, and then you find the argument and find the argument in terms of that variable or that unknown, and equate that to the given argument. You have these complex numbers u and w. They're defined like this. They want you to find u squared over w. First of all, that's straightforward. You can look at the working for that. Now, the second part says state the least positive integer n such that both imaginary part of w raised to power n is equal to 0 and the real part of w raised to power n is greater than 0. How do you think about this? What's w? W is given to be 3e raised to power 1 over pi over 3 iota. What about w raised to power n? You can put whole power n on that, and that gives you 3 raised to power n and e raised to power n or n pi over 3 iota. What's the argument that you get from this? The argument is n pi over 3. Now, if the imaginary part of this is 0, that means it has to be on the real axis, right? It has to be on this real axis. Real part is positive, that means it has to be on the right side. It has to be on the right side of this. So it's on the real axis on the right side. Now on the real axis, what are the possible angles that you can have? You can have 0, you can have 2 pi, you can have 4 pi, and so on, right? They want the least positive integer value for n. You can try 0, you can put n pi over 3 equal to 0, that gives you n equal to 0. That's not what we want. What we want the positive value. You put n pi over 3 equal to 2 pi, and that gives you n equals 6. That's the least positive value of n that we get, and that's the final solution. Okay. Then you have this Argand diagram. You had to find this locus and then find the greatest value of argument of z. Greatest value of argument of z would be at this particular point. You can either find that point using the equation of circle and then use that to find the argument, or you could use circle properties by making a right angle triangle like this and finding this small angle here, and then saying that angle at the circumference is half the angle at the center, and then find the argument by subtracting that number from pi. You can look at this working here at this. I am too tired now to explain this. You can have a look at this later on, not that difficult. That's all that we've got in complex numbers. I hope that was helpful. We will end this here. If you have any quick questions, you can let me know.